Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. Now we move on to section 6.3, specifically on the last part of 6.3, which is about composite function and inverse function. Okay, suppose that you have two defined functions, fx and gx, and therefore the composite function is denoted as f compose g of x, where basically it is saying that I have to substitute gx into x in that function f. Okay, perhaps it will be much clearer if you look at example. So here is example 6.5. Find each of the following. So this is f compose g of x, g compose f of x, and f compose f of x. Right, we start off with question A. So what is f compose g? The value of x is 2. So basically it is saying that I'm going to substitute g equals 2 into x in f function. So I'm going to substitute g2 into x. Okay, so what is g2? So g2 is 2 times 2, which is 4. So this is g2. Okay, I substitute 2 into x in function g, so that's what I get. The answer is 4. So now I'm going to substitute 4 into function f. So I'm going to substitute 4 into x here. So now that will be -3, 4 to the power of 2 minus 3, and this is equal to -3 times 16 minus 3. So that one is -48 minus 3, which is -51. Okay, so the answer is -51. Okay, so how about the second one? So the second one is g compose of f. So g compose of f, where the value of x is 2. Basically we are going to substitute f2 into x. Okay, we're going to substitute f2 into x in function g. So our job is to find what is f2. So f2 is can be obtained by substituting 2 into x in function f. So we will get -3, 2 square minus 3, -3, 4 minus 3. This is -12 minus 3, which is -15. So now -15 will be substituted into function g. So this is going to be substituted into x in function g. So that will be 2 times -15, and the answer is -30. Next, the last example is f compose f, where the value of x is -2. So now f compose f, and the value of x here is -2. So basically we are going to substitute the function of f, where the value x is -2. So this one will be substituted into itself. So it will replace x, okay, in function f. So now our first job is to find what is f -2. So this can be obtained by substituting -2 into x. Okay, so f negative 2 is negative 3, negative 2 square minus 3, and this is negative 3, 4 minus 3. So this is negative 12 minus 3, which is negative 15. Okay, now we're going to use it, and we're going to use it into this function. So now f negative 15. So f negative 15 is basically you have to just substitute negative 15 into x. So now I will have negative 3, negative 15 square minus 3. So negative 15 square is going to be positive 225. So negative 3 times 225 minus 3. So negative 3 times 225 is 675. So negative 675 minus 3 is negative 678. So this is the answer to question C. Right, next. Find G compose f of x and compare it to the results of finding f compose g if fx is given as 1 over x minus 3 and gx is 2x squared. Are the results the same? And then next, find the domain of each composite function. Right, so we start off by trying to find this guy first. So g compose f of x is actually g and having fx here. So basically you are going to substitute fx into x in function g. So what is fx? Fx is the whole thing here. You're going to substitute this into x. So now the answer will be 2. So what is x? X is 1 over x minus 3 square. Okay, so next it will be 2 times 1 over I'm sorry, let me just erase that. Oops. Okay, so that would be 2 1 over x minus 3 square. Okay, I don't need actually this bracket, so this actually will be 2x minus 3 square. Okay, now how about f of g? F compose g of x. So now we're going to look at f compose g of x. And this is actually f, this is gx, which is saying that I have to substitute gx. So this is my gx. I have to substitute that into x in function f. So that would be 1 over, so x here will be substituted with gx, so that will be 2x squared minus 3. So obviously we don't get the same result. Okay, we don't get the same result. Excuse me. Now the next question is to find the domain of each composite function. So the domain, what is domain? So domain is basically all the values of x that you can use for as long as the function is workable. Okay, now you can see that for this one, for the first result that you got over here. Okay, so for the first result that you got over here, this one, you can see that the function only works if the denominator here is not 0. So that is the crucial point that you have to pay attention to. So the function works if x minus 3 square is not equal to 0. And based on this, you can say that therefore x minus 3 cannot be equal to 0, x cannot be equal to 3. So as long as other numbers are used, it is fine, but cannot be x equals to 3. So this is the domain for the first composite function. How to properly write the answer? You can write it in terms of domain of G compose fx is all values of x. X can be real number. You can take from negative infinity to infinity, except that x cannot become 3, because when it is 3, then the denominator here will be 0, then the function becomes undefined. In other words, the function is not workable anymore. Okay. Now, how about the second one here, domain of this one? You can see similarly, because we have something over something, so the denominator part again cannot be 0, because if you divide something with 0, then you will be having some trouble here. So we have to make sure that 2x squared minus 3 cannot be 0. So this gives us 2x squared cannot be equal to 3, and x squared cannot be equal to 3 over 2. And how do I get rid of this square? I can get rid of it by introducing the square root on the left hand side. So I have to also introduce square root on the right hand side. Don't forget the plus and minus sign. So finally we have x. So finally we have x cannot be equal to plus minus 3 over 2. How to write it formally? We can write the answer formally as domain f compose G of x is equal to the value of x such that x must be real number. X can be whatever value from negative infinity to infinity, it's okay. You can punch in the value and the function will work just fine. But x cannot be positive or negative, so 3 over 2. So this is the rule, and if you have this number, the function is going to have a problem executing the output. Okay, next we are going to look at the idea of inverse function. Okay, so now we're going to look at this idea of inverse function. Okay, inverse function is a specific function where that particular function must be one-to-one function. So if you have a one-to-one function, then you will be able to find the inverse function. So this is the notation of inverse function. Okay, it doesn't mean 1 over fx, so it just means this is an inverse function of fx. Okay, it's not this one. Yeah. So inverse function has to be one-to-one, as you can see from this simple diagram. So this is A is the input, A is linked to B is the output. A is linked to B by this function called f. Okay, so this is a function called f. Therefore, this one is the domain of f, and this is the range of f. Now, when you talk about inverse function means this now will become an input. This one will become an input, and this one will become an output. So basically you reverse the process, and input is linked to the output by a function, and this function is called inverse function. Therefore, this whole thing here becomes the domain for inverse function, and this one becomes the range for inverse function. And as I said earlier, you can only have inverse function if the function is one-to-one. So what if the function is not one-to-one? So if the function is not one-to-one, the domain of the function has to be restricted such that the portion of a graph is one-to-one. Therefore, after that, then only you can find a unique inverse function for that portion. As an example, if I have the following function, fx is equal to x squared, where x is real number, basically it is saying that x can take the values from negative infinity to infinity. So if I draw this, the shape of this function, this is x, this is fx, so this is how fx is equal to x squared looks like. Now this is not a one-to-one function because, as you can see here, when, for example, if I have x is equal to 2, this function will give the value of x as 4, for example, because 2 to the power of 2 is 4. The same thing when I have negative 2. Negative 2, if I substitute into x here, I will get the same result, which is 4. So this is an example of not one-to-one function, but many-to-one function. So in this scenario, you cannot have a unique inverse function. So the solution is, when the function is not one-to-one, recall that function can either be one-to-one or many-to-one. This is the definition of function. But for inverse function, the function must be one-to-one. If it is not one-to-one, for example, like this one, this is many-to-one function, then you have to restrict the domain so that the portion of the graph is one-to-one. So what does it mean by restricting the domain? It means that the domain here, for example, instead of saying that x can take any real number, we can actually restrict the domain by saying that x can only be greater or equal to 0. So when you're talking about the domain of x greater or equal to 0, that means you are just concerning with this part of the graph, x greater or equal to 0. And based on this, you can see that we have actually changed from many-to-one function to one-to-one function. Each value of x corresponds to one value of y. For example, if x is 2, the value of y is 4. X is 0, the value of y is 0, and so on. Now, to help in understanding the idea further, let's consider a simple function that is made up of all these following points. So 1, 0. Again, this is your x, this is your y, this is your x, this is your y, this is your x, this is your y, and recall that x are referring to the input and y is the output. Okay, so this is the point. So this is the point of 1, 0. So this is 1, 0. This is the point of 0, 4. So this is 0, 4. And this is the point of negative 3 and 5. So this is 5. This is negative 3. So use a graph to visualize the points. Well, the points are already drawn here. Next, what do you think are the points seen in the inverse function? Now, recall that what you have seen here, inverse function is a very simple idea. You just reverse the process. If this is input, if in function f, this is input and this is output, in inverse function, b will become input and a will become the output. So it is saying that for this one, this is the input and this is the output. Input, output, input, and output. This is in function f. So if you are interested in finding the inverse function, basically the points in the inverse function will be 0, 1, 5, negative 3, and 4 0. Basically you are changing the position of input and output. So your output here will become the input in the inverse function. So 0 will become input now, and 1 will become the output in the inverse function. So these are the points that you will see in the inverse function. Now, can you plot the points of the inverse function on the same graph? Of course, I can do that. So now let's do it. 0 and 1. So 0 and 1. So you're talking about this point, 0 and 1. Next, I shall have 5 and negative 3. 1, 2, 3, 4, 5. Negative 3, negative 1, negative 2, negative 3. So this is another point. Negative 3. This is 5. Okay, next 4 and 0. So 1, 2, 3, 4. 4 and 0 will be here. So this is 4 and 0. Okay. Okay. Now, what is your conclusion? So after you have plotted the points, I hope that you are able to see that these points are reflected, okay, are reflected along the y equals to x line. Okay, so if I draw y equals to x, okay, y equals to x means you have a straight line that passed through the origin. So this is y equals to x. Okay. Okay, so I hope you can see that each red point is reflected to along this y equals to x. So this is y equals to x line. So the same thing with this one. It is reflected here. And the red one. So this is the conclusion that you can make when you talk about the inverse function. It is about a reflection of the points along y equals to x line. Okay. Next, find the inverse function of the followings. So if you have, this is fx. So the question is asking you to find what is the inverse function of fx, which is given by f. We have negative 1x here. Now, simple steps to find the inverse function are given by this. So first of all, you have to replace the given function fx with y. This is done so that it is easy for you to see later on. We already know that y is equal to fx. It is a common representation of function f. So now the first step is replace fx with y. Now, the next step is to switch every x to y and every y to x. Why are you doing that? Well, it goes back to the different idea, to the simple idea of inverse function, where here is the input, now is the output in f. But if you are talking about inverse function, this becomes input and this becomes output. So you are reversing the role of input and output. So this is what we will be doing here. You're going to switch. X will become y and y will become x. Next, you're going to solve for y, okay? Because y is what you're looking for, and y is actually the new inverse function. And after you are done with solving y, you're going to replace y with this notation of inverse function. Very simple. So let us try and do the first question. Okay, so the first question is A, fx is equal to x squared plus 3, and x is a real number. That means x can be from negative infinity to infinity. And for this one, actually, there is no solution for this because this function is not one-to-one. Okay, so cannot find the inverse function because this is not a one-to-one function. How do I know this is not a one-to-one function? Well, this is well, if you look at this function, this is just a variant of y equals to x squared, and you have seen that y equals to x squared, it looks like this, but you can see that this is a many-to-one function. And if you have y equals to x squared plus 3, you will have this graph translated 3 units up. So this is at this point. So again, this is a many-to-one function, and because of that you cannot find the inverse function. Now you'll be seeing a lot of sketching in the last section of this chapter. So at this moment of time, let's just not worry about it so much yet. Next, we're going to try and solve question B. So fx is equal to 1 over cert x, and x is specifically real number, and to be more specific, it is a positive real number, so from 0 until positive infinity. And again, if it helps, let me just sketch how this function looks like. So it basically looks like this. Okay, basically looks like this. So this is your x, this is your fx, and since you're talking about real positive numbers, you're talking from 0 towards positive infinity. Okay, so clearly based on this, you can see that this function is a one-to-one function, and so you should be able to find its inverse function. Okay, so what we do is, the first step is to replace fx with y. So here I'm going to have y is equal to 1 over cert x, and the next step is to switch x and y. So here will become next, then x is equal to 1 over cert y, and then we're going to try and solve for y. So y will become a subject, so I'm going to have x cert y is equal to 1. Cert y is 1 over x. So how do I get rid of the square root? Is by introducing square on the left hand side, and the same thing on the right hand side. So then I will have y is equal to 1 over x squared, and so this is the answer. This is actually our inverse function, and to complete the whole process, we are going to replace y. Therefore, y with inverse notation. Okay, we're going to replace y with inverse notation. So then this is what we will have. Okay, 1 over x squared. Alright, okay, I guess that's the end of section 6.3. Thank you very much for listening.